I hope you'll find a lot of material sounding familiar in this assignment. We review first Extrema, which we've already covered once. So remember that global and absolute are synonyms. So we'll look at this graph, and the lowest y coordinate I see is here. So we could say that there is a global min of 2 at x equals 6. And maximum can be at a closed endpoint. So right here is the highest y coordinate I see. So I would say that there is a global max of 6 at x equals 8. And local minima, the point that was the global minimum, is also a local. Remember that it can't be at an endpoint. It has to have x coordinate neighbors. And this is the only local minimum. So you might say, should we consider this endpoint? But according to our textbook, this is one that different authors handle differently, but according to our textbook, we would only have a local minimum of 2 at x equals 6. And local maximums, here we have a local, and our global maximum cannot be called local because it's at an endpoint. So we only have one local maximum, and that looks like it would be 5. A local max of 5 at x equals 3. So, sorry, let me pause. All right, I'm back on the correct page here of notes. One more time here. We've got an open point here, so that can not be a maximum, and we cannot specify. So you might say, well, isn't 2.999 repeating? Isn't that a maximum? But in fact, 2.9 repeating is mathematically equivalent to 3. So there is no maximum in this area. So this point right here can't be a maximum either because, of course, it has a higher coordinate on the left-hand side. So the only things that we've got in the running here would be a global minimum, and I think we have nothing for the others. So there is a global minimum of 0 at x equals 2, and there is no way that we can name an absolute maximum. And the same thing for local minimum. We can't go at an endpoint, so none. And local maxima, and again, we might consider only this point up here, but there is no highest value because it's an open point, so we'd have to say none. All right, so in one more case here, we want to do global or absolute minima first, and it looks like this point is a little bit lower than the others. So notice how this reads differently. At what x values do they occur? And we don't even have any coordinates on the y-axis. So we know that there is a global minimum, and I guess I'm doing this out of order, a global minimum here at a, so a global minimum at x equals a. So we don't know what the y coordinate is. Global maximum looks like this point is higher than any other. So a global max at r. Local minimum. This point right here cannot be named because it's an open one. So there's no local minimum there. But there is a local minimum here. So local min at x equals d. And local max. Well, our global is also local, and because it has neighbors on both sides. And the other question then would be this point right here, and it does have neighbors. This point right here has an x-coordinate just smaller than it, and this point right here has an x-coordinate just larger. So there is a local maximum at B. So a local max, two different places, at x equals B and at x equals R. Our global max is also a local max. All right, what about a constant function? So between 1 and 2 on the graph, so we're at a height of 7, so a constant function on a closed interval. What can we say about its extrema? Well, certainly 7 is the highest y-coordinate we see, and 7 is also the lowest value. So remember how we had to handle this, that the local cannot be at the endpoint. So there's a local max and a local min of 7 at all x in the open interval from 1 to 2. And there is a global max and global min of 7 at all x in the closed interval, because the endpoints can be included for globals. All right, a reminder of what absolute value does to a function. So we know that x squared minus 5 would be this parabola with its vertex down here at -5, but the absolute value takes any of the coordinates that were negative and flips them up to be positive. So we've got our point here at 0, 5, and we have a closed interval here from -3 to +3. So this is an even function, so think about putting 3 in for x. So f of plus or minus 3 would give us the absolute value. So we know these endpoints are at 3, 4, and at -3, 4. So they are not going to be in the running for global extrema, and local extrema cannot happen at endpoints. So what do we have here? We have a local and global max of 5 at x equals 0, and we have local and global min of 0 at, and now we've got to figure out what we have here. Where is this function equal to 0? Well, that's easy enough. Where is x squared minus 5 equal to 0? So do you see that that has to be at plus or minus the square root of 5? So just set your function to 0 to find these two x-intercepts. All right, critical numbers. Critical numbers are where the first derivative is equal to 0, or where the first derivative is undefined. So looks like I got carried away here with two f of x's. F prime of x, you can see why the fractions are there to give us a nice derivative. So power rule, the 1/4 and the 4 will cancel. The 1/3 and the 3 will cancel. And are there any values where the first derivative will be equal to 0? If this is factorable, you might have to do quadratic formula in some problems, but many times to keep this moving quickly, they will be factorable. So our critical numbers, f prime of x is equal to 0 at x equals, and it'd be nice if you put them in order, -2, 0, and 3. So 3 different critical numbers. There are no critical numbers where f prime is undefined. But look at number 7. That will come up in number 7. So we already have the derivative given here. So for our critical numbers, f prime, and we better say that we have critical numbers in two categories. F prime of x is equal to 0 when the numerator is equal to 0, so that would be at plus or minus 2, and f prime of x is undefined. There's a vertical asymptote, in other words, at -1. The importance of those undefined values is that concavity can change around an asymptote. We can switch from rising to falling, so the undefined values are important as well as the places where the first derivative is equal to 0. All right, so to repeat our definition of critical numbers then, any number in the domain, I always think this is kind of odd because if f prime of c is undefined, it might have been undefined also in the original function, but then the first derivative wouldn't exist. So that's why we have to clarify that. And the extreme value theorem, if f is continuous on a closed interval, then there has to be an absolute minimum and an absolute maximum. I read those backwards. At some values, at some c and d, and they have to be somewhere in the interval, and they could be at the endpoints. So remember to keep those endpoints closed. So the global max, the global extrema can be at the endpoints. Can be at closed endpoints. So it's very important that you don't put parentheses there. All right, Fermat's theorem. If f has a local min or max at c, and what we mean by that is at x equals c, and if the first derivative exists, then it has to be 0. So maxes and mins happen at horizontal tangents. So if there's a local max or a min, and if the derivative exists, so it could happen at a discontinuity or corner, place where the first derivative does not exist. But if the first derivative exists at a local max or min, then it has to have a horizontal tangent, is what that's telling us. All right, number 11, you want to make sure you're familiar with these. Again, when you see x squared, and then the cube root, so another way of writing this, of course, would be to say the cube root of x squared, or you could do the cube root first and then square it. Same problem. So you can see that this is an even function, as opposed to, we know what a cube root graph looks like. So let me erase this in a minute, but this is what we know about our common functions. This is the cube root of x. So what's the difference in this problem? Well, the difference in this problem is that we're going to square the value. So once we get larger outside of -1 and +1, when we square it, it will get higher. And when we square it, it will become positive. So this graph of the cube root might be a helpful way for you to remember this function that we're graphing here. So it's going to get higher there, and then it should look familiar to you that it's even, so it has to have symmetry. And there's our seagull. All right, so what do we know if we go just from -1 to +1? So I maybe graph that a little wide there, but let's think about our y coordinates. 1 to any power is still 1, so -1. The cube root would be -1, but then we're squaring it, so we would be at +1 there. So what do we know about the extrema and the critical numbers? Well, we could do extrema first. It has a global and a local min of 0 at x equals 0. And it has global max at our closed endpoints. So global max of 1 at x equals plus or minus 1. And there's no local max. You might think that goes without saying, but I think it's probably safer to explain. If you're asked to give all of the extrema, it's probably best to clarify that you've looked at all 4 types of extrema both global and local. All right, then we're also asked about critical numbers here. So we have to do f prime of x. On a recent quiz, some of you had done this problem when it actually was x to the 1/3. So by our power rule, we bring down the exponent, subtract 1. So another way of writing this, of course, would be to put the cube root in the denominator. So notice that at 0, f prime of x is undefined. F prime of x is undefined at x equals 0. F prime of x is never equal to 0, though. So our only critical number would be 0. And we have a question then of would the extrema change if we had open endpoints? Yes, if we had open endpoints. So let's see where I can squeeze in that answer. If on the open interval, then there would be no local or global maxima. That would answer that, since we would lose our closed endpoints. They would be open endpoints. All right, so again, a reminder on endpoint extrema that if you have a closed interval, your global max and mins can be at the endpoints. So a very important type of problem comes up then. If we're finding extrema on a closed interval, let's be very specific about these steps, and you'll practice them in the problems coming up later on this worksheet. So what if we want to find extrema? Well, extrema can only happen at the critical numbers. So we have to find out where is the first derivative undefined, or where is the first derivative equal to 0. And then we're going to calculate the y coordinates. In other words, that's the f of x value for each of them. Find the y coordinate. And then we also want to calculate the endpoint values, or maybe we could be more specific, the y coordinate at endpoints. Oh, I'm sorry, I'm not reading ahead here. F of A and F of B, I guess that's pretty clear. Those are the y coordinates. So I think all we need to say here is endpoints. All right, and then we know that the global or absolute max and the absolute min, I'm doing that in this order so that it matches relative terminology here. The absolute max and absolute min are the largest and the smallest of the values that we found. So let's see what these 4 steps do here in question 16. All right, so when you see that we're looking for extrema, we're looking for absolute extrema on a closed interval. So you don't have to write this each time, but this is the closed interval test. So our first step is to find the critical numbers. So I find the first derivative. And there's no undefined values, but I do think I'll be able to factor this. And I better keep the signs correct here. X minus 2, x plus 1. So our critical numbers would be -1 and +2. So now what we want to do, just like when you were a freshman in algebra, now we want to test the y coordinates at our endpoints, -2 and 3, and in between them are our 2 critical numbers. So we find the y coordinates at the critical numbers and at the closed endpoints. So this is, there's only 4 points that could possibly be the absolute extrema. So we're going to find these values in the function. And if this is not in a calculator section, then, so if I put -2 into original function here, I'd have to do some arithmetic. If it's in a calculator section, then put the function into your calculator and let it find these values. So to save video time here, I know you guys could find these. So then we've located our absolute max and our absolute min. So we know that f has an absolute max of 7 at x equals -1, and f, not f prime, f has an absolute minimum of -20 at x equals 2. So that's the closed interval test. You have to find the y-coordinates at the closed endpoints and at the critical numbers. And I think the rest of the worksheet will be your homework. So I think I will pause here and do your homework problems in a separate video.